Okay, this video we're going to finish up the fatigue part of chapter 8. So what we're going to do today is try and predict the lifetime for fatigue case. So before we jump into this slide, I want to just remind you of our fracture mechanics equation because we're going to be using this again. So again, the stress intensity is defined as, again, this geometric factor times the applied stress, remote stress, and the square root of pi times the crack length. All right, so when we're talking about having a cyclic load with some mean value and having a maximum and a minimum load, right, we have our delta sigma here, which is just max minus min, and then we have our, again, our stress amplitude, which is just delta sigma divided by 2. So while that cyclic load is going on, remember our crack A is advancing, it's growing and becoming larger. Right? So A is increasing during this cyclic loading. Well, that means, so if my cyclic loading is delta sigma, right, and my crack is growing, that means I'm actually having an increase in my stress intensity. Right? So we can speak about a stress intensity maximum and a stress intensity minimum, just like we had for the cyclic loading. The only difference now, notice, is that this maximum stress intensity has continued to rise because in time we have an A crack length that's increasing. So I'm just using my stress intensity equation. The Y is left out, set equal to 1 for simplicity, and but we'll get this increasing stress intensity. So you can kind of see, I hope physically, what's going on then is as the crack keeps advancing and the stress intensity keeps getting higher and higher, right, at some point it's going to exceed the fracture toughness, K1C, and at that point, as soon as it exceeds that, we have brittle fracture. Okay, so what the data that we need to predict the lifetime is we need the crack growth rate per cycle. So how fast is the crack growing during every cycle of our test or a real life component? And so what we've got plotted here is data from one of these fatigue tests where we're measuring, usually with a camera or something. We talked about this, I think, in the last video lecture, but we're measuring the crack length versus the number of cycles. Okay? And then we're going to go ahead and plot that versus the stress intensity, delta K, right? Where through the experiment, we know what A is, the overall A, as well as this change in A. So we need that to find this delta K value. And so most of the lifetime of the sample is spent in this middle region here, where the crack growth rate rises like a power law. So the crack growth rate itself is increasing with time. Okay. So this is the equation that would fit that region. We've got it here for you. And M is somewhere around 3 for the metals. And so this is the behavior that we need. We need C, which is a fitting parameter, and M, which again is also simply a fitting parameter. So let's go ahead and take a look at an example. Let's say that we had a polystyrene ruler that was loaded as a cantilever with a cyclic force that varies from 0 to 10 newtons. All right, so this means we have a polystyrene ruler. It's hanging over the side of our desk, and we're sitting there just kind of playing with it. So when we're not pushing down on it, it's at 0, and then when we push down with our maximum deflection, it's 10 newtons. And what we'd like to know is what depth of a transverse crack. So we put a crack on the surface of it right at the edge of the desk. Okay, so we slice it a little bit. There's a scratch there that we put there with a razor blade, for example. And we want to know what depth would this have to be for us to see fracture at 10 newtons. And then once we know this critical size, then the question is, if we have a crack of a depth, say, of 0.1 millimeters to start, how many cycles would it take before the ruler actually fails by fatigue. And we have the data here for the fitting parameters. N, I believe in the last slide we used M, and we've got C. All right, so for this bending case, then we're going to be using this stress 6 times the moment over B squared times T. Now I want to be a little bit careful here. Following this sketch here is good. Now note that with our ruler case, right, this crack here is across the width of our sample. So this T is really the width of our sample. And this B case here is really the thickness of our ruler. Okay, this is just the way that our geometry is set up. So if we're using T for thickness, then things get really confusing. But this should become thickness, which will probably end up being T, times T in this picture, which is W, the width of the ruler. All right, so let's go ahead and get back to our example. So remember, we're going to be looking at a T squared W in our example, W being the width of the ruler, and then T being that thickness. All right, so here's our stress equation. The moment is just the force times the length. So the length might be something like half the millimeter length or so, maybe 6-7 inches, depending on how much we hung over. And then we've got, again, our thickness squared and our width of the ruler. And so if you plug in some parameters for that, shown here down at the bottom, we get something like 28.4 megapascals. Okay. We can go ahead and use the fracture toughness for polystyrene that we look up, and the Y value in this case is 1.1. So we can go ahead now and plug in the fracture toughness, the Y, and the stress, and we'll get our critical crack length of 0.33 millimeters. Now I should mention that the stress that we're actually measuring here is that max stress, right? It corresponds to the 10 Newton force. And that's the one we want to use when determining what the critical crack length is. And so on the next, if we did have that crack length, then on the following cycle, as soon as we hit the max 28.4 megapascals, we get fracture. All right, so we got that. Now I'm going to come back to our data for the crack growth rate. And again, N in this problem was 4, C was 5 times 10 to the minus 6. And this is the case when our sigma is in megapascals. So this is one of those equations that, the C and the N aren't given units, particularly the C value. So we just have to make sure that when we're using the equation for the delta K in here, that we put sigma in terms of megapascals. That's what we're told to do. So don't convert this to pascals, or you won't get the right answer. A, the crack length, can be in meters. All right, so we go ahead, we put in for the delta K, our stress intensity. So there's our fracture mechanics equation. Now what we need is delta sigma, the change from the min and the max. And now in our case, the minimum value is when the load is 0. The ruler is just overhanging the desk. So this term actually is 0. So if in our case, this delta sigma is actually sigma max. So then what we need to do is just rearrange this equation so that we can integrate the number of cycles versus the crack length. Okay, so we simply rearrange the above. And what we're saying is here is that we start off with some initial crack length that's given in the problem, and then that crack length will continue to grow until it reaches that critical size, which we just calculated. And then the corresponding limits then for the number of cycles is that at 0 cycles, we're at the initial size, and then the final cycles is when our crack length A reaches the critical value. And so we can go ahead and just integrate this. And we're going to get this final equation here on the bottom. And now we can go ahead and plug in everything in this equation is now known. We're going to get 330,000 cycles. All right. Now, I do want to say something about using this equation in general. You know, we've already integrated it. There's no reason to have to go through and have you integrate every single time to get back essentially the same equation. But we're going to have to make this a little bit more general. So in general, right, we need to take this sigma max n term here, right? And this is really delta sigma, not max, delta sigma to the n. Okay, it only became sigma max in our problem, but in other problems, we actually will have a delta sigma value. So change that if you're going to use that for another type of problem. All right, and that is it for the fatigue section. So I will see you next time. We're going to talk about creep.